Zachary Way, talking about taking advantage of the Gaia data.
Cool. Hi, I'm Zach Way from Georgia State, and as you can probably tell from all my questions, I really think about binaries a lot. So just to kind of frame things, we will zoom out and look at the 200 parsec sample of Gaia. So here's just the HR diagram, and if we zoom in to the late G-type and early K-type stars, we can see that we have a really nice main sequence, right? This really well-defined line of stars, and there's two clouds kind of surrounding it. If you're unfamiliar, this is because of two kind of physical effects. One is we have the equal mass binaries, which if they're unresolved in photometry, they will be brighter by about 0.75 magnitude. This corresponds to just doubling the flux. But we also have the metal deficient stars. These are stars that have fewer chemicals in their atmospheres and thus have more optical flux, and they will appear a little bit brighter. That's why the arrow is pointing up just a little bit in the absolute magnitude band. And here we have really nicely separable populations. However, when we look at the M's, things get a little more complicated, right? The equal mass binary main sequence track smashes into the single stars. And this is largely due in part to the strong dependence of the low mass star's color on metallic content. So that we have kind of this blended situation. And the result is if we have a circle and we select a random star from the field in here, we can't tell just from astrometry and photometry if this is a metal poor binary star, which has been lifted up, or is it a single metal rich star? So we have this fundamental degeneracy between multiplicity and metallicity that is tough to break. We can't break it with RUI. Here I'm showing a simulation of around 10,000 binaries following a mass ratio distribution of closely separated low mass systems from El-Badri's paper. In black, I'm showing all of the systems, but then after you do a RUI cut of less than 1.2, in red are the stars that are left. And we get a lot of the unequal mass systems because the photocenter is wiggling around. However, the equal mass systems are not picked up by this. So we still have that degeneracy problem, and we need more information from something like spectroscopy. Luckily, Gaia, in a year ago, I don't remember, sorry, the XP Spectra were released from Gaia. This is low resolution, resolving power of around 50 for 220 million stars. And these things trace out, generally, the metallic metallicity indicators in the spectra that we usually use in these optical regimes. You can see the calcium hydride band in blue and the titanium oxide in orange. And even though there's some unphysical wiggles in the XP spectra, you can see that they trace out the general shapes of these things. So we have a strong dependence of the SED on metallicity, and we have low resolution spectra that should be able to kind of be sensitive to the metallicity. So how do we do this? We start out just by asking a simple question. Can we predict the location of a star on the HR diagram just from its spectra? So we start with the spectral coefficients. If you're familiar with the XP spectra, you know that these things are a decomposition of the spectra rather than flux sampled at specific wavelengths. So we train a random forest regression on the red side of the spectra to predict absolute magnitude and color. And after splitting things up in a training and testing split, we can look at the results. Here I'm showing a difference plot. So on the y-axis is the predicted color minus the actual color on the left-hand side. In the middle is the predicted absolute magnitude minus the actual measured absolute magnitude from Gaia. And we just have our Hertzsprung-Russell diagram again. And we can see that we're covering the colors very well. This is good because the RP spectra are in the G minus RP color, right? They're just the photometry, but in the prism spectra. But we see this strange cloud above the absolute magnitude. These are things which are predicted to be dimmer than is actually measured from Gaia. These systems are overluminous, basically. And these are candidate binaries, which is cool. And you can see if we highlight them on the HR diagram, they kind of pop out in where we expect the equal mass binaries to be. If you stare at this as much as I have, you'll notice some issues. One, there's still binaries in there. That's because there was binaries in the training set, and there's binaries that we didn't reveal as overluminous in the testing set. And there's also some weird things happening with the mean and the absolute magnitude. And this is because we still have binaries in the training sample. So how do we get at them? Well, we can start with our first model and we can predict everything, label some stars as overluminous, and yank them out from training any future samples. And if we iterate, eventually what we can do is remove more and more binaries from our original sample. This is effectively the random forest regression method. We are converging on a model trained only on the single stars in the sample. And this is really neat. We end up going for, I'm just going to skip over the rest of these. After 100 iterations, we converge on the following model where we predict absolute magnitude and color for the whole sample again, have just a 3 sigma cutoff from the single stars in the sample, and we just say these are overluminous and are candidate binaries. This runs the risk of removing some extremely metal-rich M dwarfs or the young stellar objects, but if our goal is to just get a sample of single stars in the solar neighborhood and remove likely binaries, this does the trick. It works within 100 parsecs, but if we extend this out to 200 parsecs, we start to run into problems with reddening. You can see on the top left, these strong kind of biases introduced with the G-RP color. This is just reddening effects. But in general, we find that around 30% of stars within 200 parsecs are overluminous. And I forgot again, I did this in the last time I gave this talk. In the 100 parsec sample, even with the low Rui stars, we find around 12% of stars are still overluminous or candidate binaries. So we can't get all of them with astrometric cuts. Some future work. I would love to compare different predictive models. In particular, I'd like to forward model the XP spectra. I'm working on that right now. Instead of regressing down to predicting absolute magnitude and color, flip it around. Can we predict the XP spectra from a absolute magnitude and color? And we can also do some validation work. I'm part of Sloan, so we're looking at spectroscopic binaries with apogee, but we can also look at eclipsing systems. Here I'm showing the VSX catalog of eclipsing binaries. This is a catalog released by the American Amateurs. Oh, I don't remember the rest of the acronym, but it's a big catalog of binary stars. And we're covering 83% of them, which is cool. These are stars which should be overluminous because they're unresolved. However, we have some worrying biases down in the metal poor systems. You can see that we don't do super well as we get down below the normal main sequence. This is just because when we're training the random forest regression model, there's fewer stars down there. It becomes a lot harder to train and pick out those binaries. But yeah, we're hoping to get this work out by the end of the summer. Sebastian and I are writing a paper. And if you would humor me for just 1 second, I don't often get to talk in front of a big international audience like this. And I just want to mention, I've been thinking a lot about something that's worrying to me, which is astronomy's really close relationship with military contractors, to the point where at AAS, Northrop Grumman had a big banner that said, Northrop Grumman, the astrophysics company. This is something I think about a lot, and I'm very worried about it. And I would love to talk and to imagine a better future where we might not need these military contractors to do science. If you'd like to talk about the future of astronomy or binary stars, I'd love to chat. And with that, I'll take any questions.
Your point? Questions?
Mm.
Can the next speaker come down as well, please?
I'm the last one.
The last speaker, okay. Yeah. So we have lots of time for lots of questions.
Right, yeah. Hey, Brian. It's good call as we go. So you're gonna have to, I know almost nothing about machine learning, so you'll tell me if this doesn't make any sense, that's framework, but is there a way to use the GUI to improve the identification of binaries, keeping in mind that they're going to, GUIs when placing the unequal mass binaries, let's say, to use that to help for playing the jigger validate what it's doing as it goes or something.
You could do that. Oh, sure. Elliot was asking about Whether we can use Rui to help identify and pull out binaries from our samples in the machine learning methods. We could, but I would really love to have this converge on a model just connecting the spectra to the sources themselves. Rui, it could be helpful. However, I think people rely on it too much, as I will rant about a lot. I think we need to kind of think past Rui and just accept that we're not removing all of our binaries, and it's not the best indicator of binarity at all. Yeah, I would love to be independent of it and then go back and validate Rui cuts.
Hi, Zach. Great talk. Barbara Rojas Ayala from UNDA. I got a little bit confused about what you were saying that you want to do next, like that from using, I think it was the magnitudes, try to get the Gaia XPY spectrum, like that's what you were saying?
No.
No. Okay.
Sorry.
Yeah, yeah.
Oh,
Can you tell us what you want to do next? Like you want to predict what?
so I would love to compare different. So there's kind of two steps. I would love to validate that I'm actually getting binary stars, and that would be through the eclipsing binaries, through the spectroscopic binaries, and such. But there's also the different predictive models. Right now, if we go back to my model, it's maybe it's too on the nose that it's a big black box. But you can see here we're going from the coefficients to predicting absolute magnitudes. And in effect, when we iterate and we remove stars that are overluminous, we're converging on what we assume are the single stars, but you don't know precisely what you're converging on. So I'd really love to flip this around and have a generative model where instead of going from these XP coefficients to absolute magnitude and color, saying, can we generate what we think the XP spectra should be, and in that way compare our posteriors to the actual measured absolute magnitudes and colors. No worries.
Hi, Rafael Bartolotto, University of the Republic from Uruguay. Amazing work and presentation. I wanted to ask you if you know how much, because I assume the locus of those binaries should overlap with the pre-made sequence. So how much could that affect, like how much the pre-made sequence could affect the predictions?
Oh, yeah, sorry. The question is how much, so in the CMD, pre-main sequence stars overlap with the binary stars, and how much does this affect things? I don't have a way to quantify it, but I assume it would be not that much because young stars tend to be fairly rare, especially in comparison to how many binary stars we see within 100 parsecs. So with this method, they both kind of get wrapped together, which is unfortunate. But most of our overluminous samples should be binaries.
Hi, Shubhajit Karukar from NASA Goddard Space Center. My question is, there may be multiple stellar system like trinary. There are 4 components. Do any of those interest you in any way, like, or only the binary is the only thing you are especially interested in?
So the question is, am I only interested in binaries? Am I thinking, have I thought more about other things? Yes, we should talk. What's interesting is that these overluminous stars that pop out aren't just systems out on their own. If you cross-match them to Karim-El-Badri's wide binary catalog, some of them are actually hierarchical triple systems, which are super interesting. However, I don't know how to constrain things like multiplicity rates in that sense. So if anyone has ideas on how to work out the statistics of multiplicity rates in hierarchical triple systems, I'd love to hear your thoughts.
Anytime, Zach.
Oh no.
There's always announcements. That's what you're wearing. No, I'll use this one. So. Okay, so I might need my hands for this. Okay, so the first announcement, if you didn't see it on the Slack, we're gonna take a cool stars 22 wide picture just by sun